You're in the right place to explore one of the universe's greatest mysteries. Why it looks so strikingly consistent no matter where you look. What if I told you this seemingly simple fact hides the key to understanding the very structure and origins of our universe? The more we uncover, the deeper the questions become. In this video, you'll discover how the universe's uniformity helps scientists decode its past, predict its future, and understand phenomena like the Big Bang, cosmic microwave background, and dark energy, all within a framework called the cosmological principle, the universe. A vast and enigmatic expanse stretching out before us like a canvas of cosmic mystery. When we gaze up at the night sky, we are met with a sea of stars, each one a distant sun, perhaps harboring planets of its own. The universe is a place of incredible diversity, from swirling nebulae where stars are born to colossal galaxies locked in a delicate gravitational dance. But amidst this apparent chaos, there lies a profound and almost unbelievable truth. The universe, on its grandest scales, appears to be remarkably the same in all directions. This uniformity, this uncanny consistency across unimaginable distances, is one of the most fundamental principles governing our cosmos. It is a principle that underpins our understanding of the universe's origins, its evolution, and its ultimate fate. How can it be that a universe teeming with such diverse and complex structures adheres to such a simple principle? This question has captivated the minds of astronomers and physicists for centuries, leading to the development of one of the most profound concepts in modern cosmology, the cosmological principle. This principle, born from countless observations and theoretical calculations, posits that the universe, on sufficiently large scales, is both homogeneous and isotropic. Homogeneity means that the universe has a uniform distribution of matter on large scales. Imagine taking a giant cosmic cookie cutter and extracting samples of the universe from different regions. The cosmological principle tells us that these samples, while potentially containing different galaxies and galaxy clusters, would on average have the same density of matter. The implications of the cosmological principle are profound. It suggests that our place in the universe is not special, that the laws of physics we observe here on Earth hold true billions of light years away. But how did this uniformity arise in the first place? To answer this question, we must journey back to the very beginning, to the epoch of the Big Bang. The Big Bang theory, the prevailing model for the universe's origin, tells us that our universe began from an extremely hot, dense state some 13.8 billion years ago. In the first fleeting fractions of a second after the Big Bang, the universe underwent a period of rapid expansion known as inflation. This inflationary epoch, driven by exotic physics beyond our current understanding, stretched the fabric of space-time at an exponential rate. This rapid expansion during inflation had a profound effect on the universe. It smoothed out any initial irregularities in the distribution of matter and energy, much like inflating a balloon smooths out its wrinkles. The universe, once a chaotic soup of quantum fluctuations, emerged from inflation as a remarkably uniform entity, the seeds of its future structure sown but not yet apparent. But the story doesn't end there. The uniformity we observe today is not perfect. The universe is adorned with vast cosmic structures, from galaxy clusters to cosmic filaments, tracing out an intricate web across the cosmos. So how did these structures arise from a universe that started out so smooth? To answer this, we must delve into the mysterious realms of dark matter and dark energy, forces that shape the universe on its grandest scales. Imagine standing on a vast, flat plain, stretching out as far as the eye can see in all directions. The ground beneath your feet appears level, unchanging. This simple observation, translated to the grandest of scales, forms the essence of the cosmological principle, the idea that the universe, on its largest scales, is homogeneous and isotropic. Homogeneity, in a cosmological context, implies that the universe has a uniform distribution of matter and energy when averaged over sufficiently large distances. It's not about every corner of the universe looking identical, but rather about the overall density of matter remaining consistent. Think about a cup of well-stirred coffee. While individual milk molecules might be dispersed unevenly, the overall mixture appears homogeneous. Isotropy, the second pillar of the cosmological principle, adds another layer to this cosmic uniformity. It suggests that the universe looks the same in all directions, regardless of where you are observing from. Picture yourself at the center of a perfectly spherical balloon. As you inflate the balloon, every point on its surface moves away from you at the same rate. This is analogous to the expansion of the universe, an isotropic expansion where galaxies recede from each other uniformly. The cosmological principle, however, is not just a philosophical musing, it's a cornerstone of modern cosmology, supported by a wealth of observational evidence. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space. The cosmic microwave background radiation, often abbreviated as CMB, provides us with a snapshot of the universe as it was a mere 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, releasing a flood of photons that have been traveling through the cosmos ever since. When we observe the CMB today, we are essentially looking back in time to this ancient epoch. What's astonishing is that the temperature of the CMB is remarkably uniform across the entire sky, with tiny fluctuations of just a few parts in 100,000. This uniformity in temperature implies a corresponding uniformity in the density of matter and energy in the early universe, lending strong support to the cosmological principle. These tiny temperature fluctuations in the cosmic microwave background are not random. They represent the seeds of the large-scale structure we observe in the universe today. Over billions of years, gravity has amplified these initial density variations, pulling matter together to form galaxies, galaxy clusters, and vast cosmic filaments. The fact that we observe such a close match between the pattern of temperature fluctuations in the cosmic microwave background and the distribution of galaxies in the present-day universe provides further evidence for the cosmological principle. It suggests that the laws of physics, including gravity, operate in a consistent manner throughout the universe, shaping its evolution from the earliest moments to the present day. However, the story of the universe's uniformity is not without its mysteries. While the cosmological principle provides a robust framework for understanding the universe on its largest scales, there are intriguing hints of structures that challenge this notion. Observations of galaxy clusters and superclusters, colossal cosmic conglomerates spanning hundreds of millions of light-years, suggest that the universe might not be perfectly homogeneous after all. These enormous structures, if they indeed violate the cosmological principle, could have profound implications for our understanding of the early universe and the processes that governed its evolution. They might even point towards new physics beyond our current understanding, perhaps related to the enigmatic nature of dark matter and dark energy. As we delve deeper into the cosmos, armed with ever more powerful telescopes and sophisticated computer simulations, we continue to refine our understanding of the universe's structure and evolution. The cosmological principle, while challenged by these tantalizing hints of large-scale anomalies, remains a cornerstone of our cosmological models, guiding our exploration of the cosmos. To comprehend the astonishing uniformity of the universe, we must journey back to its very inception, to a time when the cosmos was an incomprehensibly hot, dense, and chaotic inferno. This is the realm of the Big Bang, the prevailing scientific theory that describes the universe's origin from a state of extreme energy density. Imagine, if you will, a universe smaller than a single atom, yet containing all the energy and matter that would eventually become stars, galaxies, planets, and even ourselves. In this unimaginable crucible, the very fabric of space-time was being stretched and twisted by forces beyond our current comprehension. It is within this primordial soup, a realm governed by the laws of quantum mechanics and general relativity, that the seeds of the universe's uniformity were sown. To understand how this occurred, we must delve into the extraordinary concept of cosmic inflation. In the first infinitesimal fraction of a second after the Big Bang, the universe underwent an exponential expansion known as inflation. Driven by an as-yet unknown inflationary field, space itself expanded at a rate far exceeding the speed of light. This rapid expansion had a profound smoothing effect on the universe, ironing out any initial irregularities in the distribution of matter and energy. To visualize this process, Imagine a wrinkled fabric being stretched taut. As the fabric expands, the wrinkles smooth out, leaving a more uniform surface. Similarly, cosmic inflation stretched the fabric of space-time, smoothing out any initial quantum fluctuations and creating a remarkably homogeneous universe. This inflationary period, though incredibly brief, played a crucial role in shaping the universe we observe today. It set the stage for a universe where the laws of physics would operate consistently across vast distances. A universe where the seeds of galaxies and stars could eventually be sown. As inflation came to an end, the universe continued to expand, but at a more leisurely pace. The energy driving inflation was converted into a hot, dense soup of particles and radiation, setting the stage for the formation of the first atoms and eventually stars and galaxies. The expansion of the universe, however, is not like the explosion of a bomb, where fragments are hurled outward into pre-existing space. Instead, it is the very fabric of space-time itself that is expanding, carrying galaxies along for the ride like markers on a stretching rubber sheet. This expansion, governed by the laws of general relativity, has profound implications for our understanding of the universe's uniformity. As space expands, the wavelength of light traveling through it is stretched, causing a redshift. This redshift, observed in the light from distant galaxies, provides compelling evidence for an expanding universe. The extreme heat and density of the early universe prevented the formation of atoms as we know them. Instead, protons, neutrons, and electrons existed in a plasma state, constantly colliding and interacting with photons of light. This plasma was opaque to light, much like a thick fog, preventing us from seeing directly into this early epoch. However, as the universe continued to expand and cool, a crucial transition occurred. Around 380,000 years after the Big Bang, the temperature had dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, marked a profound shift in the universe's properties. With the formation of neutral atoms, the universe became transparent to light. Photons, once trapped in the dense plasma, were now free to travel through the cosmos, carrying with them a snapshot of the universe as it was at that moment. These ancient photons, stretched and cooled over billions of years, formed the cosmic microwave background radiation we observe today. The cosmic microwave background radiation, often abbreviated as CMB, provides us with a remarkable glimpse into the early universe, a time when the cosmos was just beginning to take shape. What's astonishing is that the temperature of the CMB is incredibly uniform across the entire sky, with tiny fluctuations of just a few parts in 100,000. These tiny temperature fluctuations, though seemingly insignificant, are actually the seeds of the large-scale structure we observe in the universe today. They represent regions of slightly higher or lower density in the early universe, regions where gravity would eventually exert its pull, drawing matter together to form stars, galaxies, and vast cosmic filaments. The fact that we observe such a close match between the pattern of temperature fluctuations in the CMB and the distribution of galaxies in the present-day universe provides compelling evidence for the cosmological principle and the role of gravity in shaping the cosmos. The cosmic microwave background radiation is not merely a static snapshot of the early universe, it's a dynamic echo chamber that carries information about the universe's composition, geometry, and evolution. By studying the subtle patterns and variations in the CMB, cosmologists can piece together the history of the universe and test their models of its origins. One of the key pieces of information encoded in the CMB is the universe's overall geometry. By measuring the angular size of the temperature fluctuations, cosmologists can determine whether the universe is flat, spherical, or saddle-shaped. Observations of the CMB strongly suggest that the universe is remarkably close to being flat, a finding consistent with the predictions of inflationary cosmology. Over the past few decades, cosmologists have made remarkable progress in mapping the cosmic microwave background radiation with ever-increasing precision. Satellites like COBE, WMAP, and Planck have provided us with exquisitely detailed maps of the CMB, revealing its subtle temperature variations and polarization patterns. These maps have revolutionized our understanding of the early universe, allowing cosmologists to determine its age, composition, and expansion rate with unprecedented accuracy. The CMB has become an indispensable tool for probing the universe's origins and testing our fundamental theories of physics. The quest to understand the universe's origins is one of the most profound and challenging endeavors in science. The cosmic microwave background radiation, a faint afterglow of the Big Bang, provides us with a unique window into the universe's infancy, allowing us to test our theories of cosmic evolution and search for clues about the fundamental nature of the cosmos. As we continue to explore the universe with ever more powerful telescopes and sophisticated instruments, we are likely to uncover even more secrets hidden within the cosmic microwave background radiation. Secrets that could unlock a deeper understanding of the universe's origin, evolution, and ultimate fate. Imagine trying to understand the history of Earth by listening to the faintest whispers carried on the wind. Whispers originating from civilizations long gone. These whispers, fragmented and faint, would hold clues to the past, to the events and processes that shaped our planet. In a sense, this is what cosmologists attempt to do when they study the cosmic microwave background radiation. They strive to decipher the whispers of the early universe, encoded in a faint afterglow of light that has been traveling through the cosmos for billions of years. This faint afterglow, known as the cosmic microwave background radiation, or CMB for short, is a relic of a time when the universe was a vastly different place, a time when stars and galaxies had yet to form and the cosmos was filled with a hot, dense soup of particles and radiation. To understand the CMB, we must journey back to this epoch, to a time roughly 380,000 years after the Big Bang, when the universe underwent a profound transformation. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson, two scientists at Bell Telephone Laboratories, was a pivotal moment in the history of cosmology. Initially, they stumbled upon this faint microwave signal as an annoying source of noise interfering with their radio astronomy observations. Little did they know that this noise would turn out to be one of the most profound discoveries in astrophysics, providing compelling evidence for the Big Bang theory and revolutionizing our understanding of the universe's origins. Before the discovery of the CMB, the Big Bang theory, while compelling, lacked direct observational support. The CMB provided this missing piece of the puzzle, a tangible relic of the early universe, a baby picture of the cosmos, so to speak. Its existence and properties aligned remarkably well with the predictions of the Big Bang model, solidifying its status as the leading explanation for the universe's origin. To understand the nature of the CMB, we must recall that light, in its most fundamental form, behaves both as a wave and a particle. These particles of light, known as photons, are constantly interacting with matter, being absorbed and emitted by charged particles such as protons and electrons. In the extremely hot and dense early universe, these charged particles were so tightly packed together that photons could only travel short distances before being scattered in random directions, much like light trying to penetrate a dense fog. However, as the universe expanded and cooled, a crucial transition occurred. Around 380,000 years after the Big Bang, the temperature dropped below a critical threshold, allowing protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, marked a profound shift in the universe's properties. The fog cleared, and the cosmos became transparent to light. The photons that were released at the time of recombination have been traveling through the universe ever since. Their wavelengths stretched and their energies redshifted as the cosmos continued to expand. Today, these photons reach us from all directions in space, carrying with them a faint afterglow of the early universe, a thermal echo of a bygone era. This faint afterglow is the cosmic microwave background radiation. But the CMB is more than just a uniform glow. Embedded within its faint signal are subtle variations in temperature and polarization, tiny fluctuations that hold a wealth of information about the early universe. By studying these variations, cosmologists can piece together the history of the cosmos, testing their models of its evolution and searching for clues about its fundamental nature. One of the key pieces of information encoded in the CMB is its spectrum, the distribution of its energy across different wavelengths. The CMB's spectrum is incredibly close to that of a perfect black body, an idealized object that absorbs all radiation incident upon it and emits radiation based solely on its temperature. This near-perfect blackbody spectrum tells us that the early universe was in a state of thermal equilibrium, meaning that energy was distributed evenly throughout the cosmos. This finding is a crucial prediction of the Big Bang theory, further solidifying its status as the leading explanation for the universe's origin. While the CMB's overall temperature is remarkably uniform, it exhibits tiny fluctuations, variations of just a few parts in 100,000. These temperature fluctuations, though minuscule, are incredibly significant. They represent regions of slightly higher or lower density in the early universe, regions where gravity would eventually exert its pull, drawing matter together to form the stars, galaxies, and vast cosmic structures we observe today. These density fluctuations, amplified over billions of years by the relentless pull of gravity, provide a direct link between the smooth, uniform early universe revealed by the CMB and the clumpy, structured universe we observe today. By studying the pattern of these temperature fluctuations, cosmologists can test their models of structure formation and gain insights into the nature of dark matter and dark energy, the mysterious components that govern the universe's evolution. In addition to temperature variations, the CMB also exhibits subtle patterns of polarization. Polarization refers to the orientation of light waves' electric fields. Just as polarized sunglasses can reduce glare by blocking light waves with certain orientations, cosmologists can study the polarization of the CMB to learn about the processes that occurred in the early universe. One of the most exciting aspects of CMB polarization is its potential to reveal the existence of primordial gravitational waves, ripples in the fabric of space-time generated during the epoch of cosmic inflation. These gravitational waves, if detected, would provide direct evidence for inflation and offer a glimpse into the universe's first fraction of a second, a realm governed by the laws of quantum gravity. The cosmic microwave background radiation is often described as a cosmic symphony, a faint echo of the universe's first moments. By studying its temperature, spectrum, and polarization, cosmologists are essentially listening to this symphony, deciphering the notes and harmonies that hold clues to the universe's origin, evolution, and ultimate fate. As we continue to refine our instruments and develop more sophisticated techniques for analyzing the CMB, we can expect to uncover even more secrets hidden within this faint afterglow of creation. The cosmic microwave background radiation, once a serendipitous discovery, has become an indispensable tool for probing the universe's deepest mysteries, guiding us on our quest to understand our place in the cosmos. Our journey into the uniformity of the universe takes us now into a realm that challenges our very understanding of the cosmos, the realm of the unseen, the domain of dark matter and dark energy. These enigmatic entities, though invisible to our telescopes, exert a profound influence on the universe, shaping its structure, driving its expansion, and ultimately determining its fate. For centuries, astronomers have relied on the light emitted, absorbed, or reflected by celestial objects to study the universe. However, the discovery of dark matter and dark energy has revealed that the visible universe, the stars, galaxies, and gas clouds we can directly observe, represents a mere fraction of the cosmos's total energy content. The story of dark matter and dark energy is a testament to the power of scientific inquiry, a reminder that our understanding of the universe is constantly evolving as we confront new mysteries and uncover hidden truths lurking in the shadows of the cosmos. Our story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. He was looking at a giant group of galaxies called the Coma Cluster. These galaxies are held together by gravity like a giant cosmic dance. But Zwicky noticed something strange. The galaxies were zipping around way too fast. If you only looked at the stuff we see, like stars and gas, the cluster should have flown apart long ago. It was like watching a merry-go-round spinning so fast that the horses should be flung off. Zwicky had an idea. He thought there must be something else there, something we see, holding everything together. He called it Dunkel Materie, which is German for dark matter. This invisible stuff, he figured, must have a lot of gravity, enough to keep the cluster from breaking apart. At first, people didn't believe Zwicky. They thought he was wrong. But later, other astronomers looked at different galaxies and galaxy clusters. They found the same thing. Stars in galaxies were also spinning too fast. It was like the entire universe was a giant puzzle, and the pieces didn't fit unless there was this mysterious dark matter holding it all together. To understand the puzzle of galactic rotation, imagine swinging a ball attached to a string around your head. The faster you swing the ball, the more tension you feel in the string, as if an invisible force is trying to pull the ball away. This invisible force is the centrifugal force, and it's counteracted by the tension in the string, keeping the ball in orbit. In a similar way, the stars in a galaxy are in orbit around the galactic center, held in place by the gravitational pull of the matter within the galaxy. However, just as the tension in the string determines how fast you can swing the ball, the amount of matter within a galaxy determines how fast its stars can orbit without flying off into space. When astronomers measured the rotation speeds of stars in spiral galaxies, they found something astonishing. The stars in the outer regions of galaxies were orbiting much faster than expected based on the visible matter alone. It was as if the galaxies contained a hidden source of gravity, an invisible component providing the extra pull needed to keep these speedy stars in check. Another line of evidence for dark matter comes from the phenomenon of gravitational lensing, a prediction of Einstein's theory of general relativity. According to general relativity, massive objects such as galaxies and galaxy clusters can bend the path of light passing by them, acting like giant cosmic lenses. When light from a distant object passes by a massive foreground object, its path is bent, and multiple images of the background object can be seen, much like how a magnifying glass can create multiple images of an object behind it. By studying the distorted images of background galaxies, astronomers can map the distribution of matter, both visible and dark, within the lensing object. Observations of gravitational lensing have provided some of the most compelling evidence for the existence of dark matter. By analyzing the distorted images of background galaxies, astronomers can infer the mass of galaxy clusters and have found that the mass inferred from lensing is far greater than the mass that can be accounted for by visible matter alone. Dark matter, though invisible to our telescopes, is not simply scattered randomly throughout the universe. Observations of its distribution reveal that it forms a vast interconnected web of filaments and halos, a cosmic scaffolding upon which galaxies are strung like beads on a string. This cosmic web, shaped by the gravitational pull of dark matter, plays a crucial role in the formation and evolution of galaxies. The dense regions of dark matter act as gravitational wells, drawing in normal matter and providing the seeds for galaxy formation. The distribution of dark matter in the early universe, as revealed by the cosmic microwave background radiation, provides a blueprint for the cosmic web's eventual structure. The tiny temperature fluctuations in the CMB represent regions of slightly higher or lower density, and these density variations, amplified over billions of years by gravity, gave rise to the vast cosmic web we observe today. While dark matter's gravitational pull draws matter together, shaping the universe's large-scale structure, another enigmatic entity known as dark energy exerts a repulsive force, driving the universe's accelerated expansion. The discovery of dark energy in the late 1990s came as a complete surprise to astronomers and has profound implications for our understanding of the cosmos's fate. The story of dark energy begins with the study of Type Ia supernovae, distant exploding stars that serve as standard candles for measuring cosmic distances. These supernovae have a remarkable property. Their intrinsic brightness is relatively uniform, allowing astronomers to determine their distances by comparing their apparent brightness to their known luminosity. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using Type Ia supernovae to measure the universe's expansion rate. To their astonishment, they found that distant supernovae were fainter than expected, implying that they were farther away than predicted by a universe expanding at a constant rate. This unexpected dimming of distant supernovae suggested that the universe's expansion was not slowing down, as would be expected in a universe dominated by gravity, but was in fact speeding up. This discovery, one of the most profound in the history of cosmology, implied the existence of a mysterious force counteracting gravity, pushing galaxies apart at an accelerating rate. This mysterious force, dubbed dark energy, remains one of the greatest enigmas in modern physics. Its nature and origin are unknown, but its effects are undeniable. Dark energy makes up roughly 68% of the universe's total energy content, making it the dominant component of the cosmos. The discovery of dark energy has profound implications for our understanding of the universe's fate. In a universe dominated by gravity, the expansion would eventually slow down and the universe would either collapse in on itself in a big crunch or expand forever at an ever-decreasing rate. However, in a universe dominated by dark energy, as ours appears to be, the expansion will continue to accelerate and the universe will expand forever, becoming increasingly cold, dark, and empty. This scenario, often called the Big Freeze or heat death of the universe, paints a rather bleak picture of the cosmos's distant future. The fate of the universe ultimately hinges on the nature of dark energy and whether its repulsive force will remain constant, increase, or decrease over time. Some models suggest that dark energy's strength could increase, leading to a Big Rip scenario, where the universe's expansion accelerates uncontrollably, ripping apart galaxies, stars, and even atoms themselves. The quest to understand dark matter and dark energy is one of the most profound and challenging endeavors in modern science. These enigmatic entities, though invisible to our telescopes, hold the keys to unlocking the secrets of the universe's structure, evolution, and ultimate fate. As we continue to explore the cosmos with ever-increasing precision and ingenuity, we can hope to shed light on these cosmic mysteries, illuminating the dark corners of our universe and our place within it. As we conclude our exploration of the universe's remarkable uniformity, we are left with a sense of awe and wonder at the intricate workings of the cosmos. From the tiniest subatomic particles to the largest cosmic structures, the universe operates with an elegance and precision that speaks to a deep underlying order. The cosmological principle, the idea that the universe is homogeneous and isotropic on its largest scales, has served as our guiding light throughout this journey, leading us through the echoes of the Big Bang, the faint afterglow of the cosmic microwave background radiation, and the enigmatic realms of dark matter and dark energy. We've seen how the universe's extraordinary uniformity in the early universe, as revealed by the CMB, provides compelling evidence for the Big Bang theory and the inflationary epoch that stretched the fabric of space-time, smoothing out any initial irregularities. This early uniformity, however, was not absolute. Tiny fluctuations in the density of matter and energy, amplified over billions of years by the relentless pull of gravity, gave rise to the cosmic web of galaxies, clusters, and filaments we observe today. One of the most profound implications of the cosmological principle is that the laws of physics, as we understand them here on Earth, appear to hold true throughout the observable universe. The same forces that govern the motion of planets around stars also dictate the interactions of galaxies within clusters, separated by vast cosmic distances. This universality of physical laws is a testament to the power of scientific inquiry and our ability to unravel the mysteries of the cosmos through observation, experimentation, and theoretical modeling. The discovery of dark matter and dark energy, though initially challenging our understanding of the universe, has only deepened our appreciation for the elegance and complexity of the cosmos. These enigmatic entities, though invisible to our telescopes, have forced us to re-examine our assumptions about the nature of gravity, the composition of the universe, and the very fabric of space-time. Despite the remarkable progress we've made in understanding the universe's uniformity and the processes that have shaped its evolution, many mysteries remain. The nature of dark matter and dark energy, the driving forces behind the universe's structure and expansion, remains one of the most pressing questions in modern cosmology. What are these enigmatic entities made of? How do they interact with normal matter and each other? The quest to understand dark matter and dark energy will undoubtedly lead to new discoveries and breakthroughs in our understanding of the cosmos. New generations of telescopes, both ground-based and space-based, will peer deeper into the universe, revealing fainter objects and probing the cosmos with greater precision than ever before. These technological advancements will be coupled with innovative theoretical models and sophisticated computer simulations, allowing cosmologists to test their ideas against observations and refine our understanding of the universe's fundamental laws. The study of the universe's uniformity has not only deepened our understanding of the cosmos, but has also highlighted the interconnectedness of all things. We are, after all, a product of this universe, forged from the same stardust that makes up distant stars and galaxies. The hydrogen in our bodies, the oxygen we breathe, the calcium in our bones, all were created in the fiery furnaces of stars long ago, scattered across the cosmos by supernova explosions and incorporated into the gas clouds that eventually gave rise to our solar system and life itself. As we continue to explore the cosmos, we are not merely answering questions about the universe's origin and evolution. We are also gaining a deeper understanding of ourselves, our place in the grand scheme of things, and our responsibility to preserve and protect the fragile planet we call home. The universe, with its vastness, its beauty, and its mysteries, beckons us to continue exploring, to push the boundaries of our knowledge, and to embrace the wonder and awe that inspire us to seek answers to the most fundamental questions about our existence. And so our journey into the universe's uniformity comes to an end, but the quest for knowledge and understanding continues. We invite you to join us in this grand adventure, to ask your own questions, to explore the cosmos with open minds and curious hearts, and to never stop marveling at the wonders of the universe we are privileged to call home. Thank you for joining us on this journey through the universe. Please like and share the video, and please do not forget to subscribe for more videos.